meaningful and inspiration data integration, which will be about Edelweiss, Rosiglitazone, CSV files, and linked data. So Edelweiss is a working name for our technology in progress, which is currently under development. So even though it's not finished, we have some prototypes and some mock-ups to show you. And we hope we can convey to you today a feeling of how exactly this is supposed to work in practice. And to start things off, so just to talk about the data integration problem a little bit to set the context, which I think is a problem everyone is facing in bioinformatics or everyone who works with any kind of data science. And the problem is that everybody is making data sets in various laboratories, in various research groups, but it's hard to use any major data set, whether it's your own data set or it's a public data set, without any integration. The reason why you need integration is you need to have a context for your data. The context will support hypothesis formulation, validation of, am I using data in the right way? And it will let you understand what you're looking at. So data is not useful by itself, in other words. And also data integration cannot usually be added as an afterthought. You cannot post facto say, oh, I forgot to integrate this data, because the process really begins at data capture. The person who is in the lab and operating the equipment is ultimately the one who has the best knowledge to annotate that data properly. And such annotation supports the integration later on. And recently, there's been a lot of talk about a way of thinking, which is called FAIR, about data science. FAIR stands for findable, accessible, interoperable, and reusable. And this is also ultimately about data integration. How can we use data meaningfully, and how can we combine it with other data sets? So this, even though it sounds like a technical problem, it's actually a very real and very practical concern. And so to give that a little more flavor, we can think about the whole dataset lifecycle. So what happens to data after it's been captured in an assay or an experiment? So often what happens is data is annotated, and then it may be published. It may be integrated with other data sets. And then after integration, it may be used, or it may be built upon to create maybe an application, or to maybe create a study, or to create maybe a derived data set, or to do other things. And so far in DC, in our existing offerings with OpenTox and with our technologies, we already have some solutions that address some parts of this life cycle. We have the OpenTox APIs, which help with data publication. We have Garuda, which allows for data integration and which allows you to apply various discoverable analytics to your data set. And we have a Data Explorer and a Jupyter Notebook, which allows for practical use of your data, whether it's in an application or it's by users on the internet interactively. So there are various components here, but we're not yet there, and we can still do more, we think, because there are still problems of communication between groups. There are many practical bottlenecks to actually getting your data into this whole system. People have different identifiers for the same concepts. It's hard to discover related and relevant data. How can I discover data that is related to my random CSV file I have just generated or just discovered somewhere? And even though there are solutions such as ontologies and ontology terms out there, many of them are too specialized or too technical for daily practical use. So the solutions that are there, both from Douglas Connect and from other groups, are not quite solving all the problems in this area yet. So we can do more. So one technology that seems promising and which can maybe help a little bit is something called linked data. So this, again, will sound a little technical at first, but it will become very practical if you bear with me. And the trick of linked data is very simple. We turn a single identifier string, which can identify something like a protein or an organism or a tissue or a compound, into an IRI. So IRI means Internationalized Resource Identifier. It looks like a URL. And this makes sense because the URL system was the original global namespace, as it were. So if you put your identifiers into the system, there's already a way to disambiguate between countries, between organizations, because every organization has their own domain, and you can add paths to every domain. And this is already a standard that exists. So it makes sense to organize data in this way as well. And linked data is actually a standard pushed by W3C, which is the organization that supports the World Wide Web and HTTP standards. So this is already being used by many major data providers. So in life science, you see this used by Uniprot, you see it being used by KEG, you see it being used by Drug Bank and various others. and it's coming more and more. So the problem is, even though this technology is there, it's still not as practical to use as we might think. But even so, it is growing very quickly. So looking back at how much we've got, this is a visual image that you can see on the web if you go to this website that shows you what is the linked data out there. And as you can see, it looks like a giant brain. And this is probably in some people's heads, this is probably the image of what linked data should be like, that it should be like a giant brain. And in this image, they've been divided by, the various ontologies have been divided by subject field. So some of them are life science, some are government, some are cross-domain, some are geography, and so on. And you can see the largest part is life science in here. So a significant chunk of all the linked data that is out there is life science data. And this is tissues and diseases and proteins and whatnot. And you can find all that concretely if you go to this website. So the remaining difficulties, as I said, there are remaining unsolved problems. One of them is still tedious and hard work to convert all my data into IRIs. So ordinary people, or most people, let's say, are not going to rewrite their data in this format. And for daily work that I do day by day, I just want to look at the data. I don't want to look at IRIs. And also, even if I have the IRIs, I still don't know how to discover the relevant external data sets to integrate with. And these are the problems that we think we can solve in Douglas Connect with Edelweiss. So concretely, what we're doing here, if we can solve these problems, we think we can come across this bottleneck here and bridge this chasm. And this is the chasm because in practice, we think what happens is a lot of data gets captured in an experiment or assay, and then it just sits there and it never gets any further. If it gets used at all, it gets used only in that lab by those people who made that data. But if we can make it very easy to annotate and to publish the data in some standard formats, then you would be able to get across and you'd be able to carry out all these other things like integration and all these derived applications. So these are really, if you go back to the life cycle image, these are the hardest parts to solve. So now I've been talking about these very abstract technologies and these informatics concepts for some time, but now to give that a little more flavor, I want to consider those same things again against the backdrop of a biological problem. So let's talk about a failed drug. So the case of Rosiglitazone and Troglitazone, and see what we can do with these technologies in that particular case. So as you might know, so Rosiglitazone and Troglitazone are both anti-diabetic drugs. And these slides, by the way, are due to Tissue Dynamic. They were very kindly shared with us. And they both have a very similar mechanism. They both work as insulin sensitizers, but Troglitazone is failed and taken off the market because of occasional liver toxicity and cholestasis. And Rosiglitazone is not taken off the market. There is some subtle difference between these drugs. And if I'm interested in Rosiglitazone and I'm a biologist, I might be interested in looking at these two drugs and comparing them to try to understand better what is the problem here. Also, another thing that we may note as background is that there is the metabolic profile, the metabolic fingerprint of these two drugs is quite different because in Troglitazone, lipogenesis shuts down almost completely. So it has a kind of strange metabolic fingerprint, whereas with Rosiglitazone, the lipogenesis goes on. So this may give us some hints about various things happening to certain pathways or certain proteins. So the question here is, starting from one of these drugs, if I want to know more, how can I discover relevant information? How could I discover this Troglitazone information if I didn't know from the start? And how can I understand these drugs in context without magical background knowledge? So to solve that problem, let's introduce Edelweiss. So Edelweiss is a working name. It may be renamed at some later point, but it's the current technology name. And the goal of Edelweiss is to provide you with correct, simple, and useful data integration. It should be all of these things. It should be technically correct and scientifically valid. It should be simple to understand, and it should be practically applicable to real data that people actually have. These are the constraints for the design. And the starting point for working with Edelweiss is something people often have in practice, which is you have a CSV file or a TSV file that you got from somewhere. This is probably the lowest common denominator between people's data sets, and you don't know what the structure is. There is some data in it, but you don't know what every column represents. So here in this illustration, I've made up a hypothetical little file. This is just an illustration, but this is what it might look like. So you might want to think to yourselves as you look at this, what would I do as a biologist or as an informatician to start making sense of this data? So here's where I would have had my demo, but at the moment our prototype websites are down, so I will show you screenshots instead. What I do in Edelweiss is...
Sorry to interrupt, it's up, so you can use it.
I can use it, okay, so let's go and use it. So now let's try to use the Edelweiss schema editor. So hopefully this can be a live demo. So I load the schema editor in my web browser here. Here it is. So the idea is you upload your data into the application. So I click upload, and then actually I should just drag the file into here. So here's my LTKB file. This is the liver toxicity knowledge base. I think it was dragged in successfully. And then I will call it LTKB. And then I click upload. And it uploads the data into the system. And then it's going to look at the columns it finds and discover automatically what's in this file. And then it's discovered these various columns that we found in the file. So here we're trying to find as specifically as possible what is the type of every column. So we found LTKB ID, compound name, approval year, daily concern. And currently there are some very general types available here, such as Boolean, integer, floating point, string, IRI. And later on, there will be also more specific ontology types. So we do a best guess, and we try to figure out the structure of that file as well as we can, and put it in here. And eventually, for example, smiles will of course be something that will be guessed automatically. And then you can select for every field, should it be searchable or not searchable? Should it be aggregatable or not aggregatable? So you make your settings, but there will be good defaults for you. So in the best case, you shouldn't have to do very much at all. And then once you're happy with your settings, you click Save and Publish. And Save and Publish will automatically generate for you a data explorer. You can also get this data that you just uploaded from Python or from any other programming language by using this demo code. So we go to the data explorer that we just generated. And there will be a couple of data sets. And hopefully this will still be up here. So let me try to reload this page and see if that works for reloading. Okay, I don't think the dataset is available right now. We'll check back in a minute. But you can imagine, if you like, it looks like this. The Data Explorer you may have already seen by Douglas Connect, with an LTKB tab here as well in addition. And that shows you in real time the data that you've uploaded, and these columns here are available as you edited them in the schema editor that we saw just now. So just back to the presentation. So this was the schema editor, and then you got a Data Explorer, and it would look a little bit like this when uploaded. And so what's just happened here while I did this was the following. We upload the unknown data. It goes into the Edelweiss schema discovery, which is discovering, as well as it can, what's in the text file. And then it integrates the data. Actually, I'll get back to data integration later. I'll demonstrate that later. And then it goes into storage, and then it goes into APIs and Data Explorer, and becomes available in various ways. And the idea later as well, which I will show later, is to integrate this data with other linked open data from known ontologies that are available on the web to the public. So you'll see it in a bit. But what we did just now, just before, was the schema discovery part. So the concept of Edelweiss here is by storing information about common identifiers. So we look, for example, at what's in the field and what is the pattern of what's available in every text field in that file. In the life sciences domain, we can mostly guess the content of any text file. This will become clear in a moment. And by mapping such identifiers to ontology terms, i.e. the IRIs I showed before, we can turn any text file into linked data automatically. and we can integrate them with suitable data sets automatically. So that's the first part here, the schema discovery. So let's get on to that and let's break that down. So here is a much smaller table, a smaller subset of data. So here are 4 values: ANS must 000-31399, the Q9Z324, 008152, 31. If I am a smart bioinformatician, what can I say about these values? What do I know about them? Well, probably the first one looks like an ensemble gene. It could be something else, but I'm 99% confident it's an ensemble gene because I've seen them before and I know that they look like this. Similarly, I can guess that the second Q9Z324 is probably a uniprot protein. Based on the context I'm seeing it in and based on what it looks like, because I've seen such strings before as well. Similarly, I may guess that this third value here, 0008152, it could be a geoterm based on the length and the formats. But I'm not as confident about this because it's quite generic and it might be something else as well. But let's say I'm 60% confident that it's a geoterm. And then I see a number 31. And that's of course useless because without any further context, I don't really know what 31 means. So sometimes by looking at the pattern, you can really guess what it is, and sometimes you can't. So context helps, and patterns also help. So Edelweiss, to help with this, has a knowledge base which thinks about what it sees. So if I see a column that contains only these 3 values here, Q3V493, Q9ES56, Q544R8, then Edelweiss will think, oh, I think this column has uniprot proteins. So it has made a conclusion based on what it sees in there. If it sees this column here at the bottom, 1234 Q9ES56 NM12390, then it is going to think, oh, I recognize a few things here, but I don't see a pattern. So there is a degree of confidence involved, and maybe in practice you want to allow a few mismatches per column, but not too many. But the idea is to see a common pattern for all the values in every column. So now we go back to this table I showed you before, the table with the unknown structure. So what can we identify here? We apply the Edelweiss inference engine, the Edelweiss knowledge base, to see what it finds. And it successfully identifies 3 columns, the ensemble gene, the uniprot protein, and the PubChem CID by looking at the pattern in this data. However, it fails to identify 1 column, the negative and positive column, because we don't really know what's in there. And the geoterm column we kind of identify, but we maybe warn the user, this is a tentative guess and you might want to validate this. So we have a degree of confidence. But still, we successfully discovered 3 columns, so that's pretty cool, and we can do something with that. The next step after you've discovered a couple of columns is to try to discover external data as well, to give more context to your data sets. So Edelweiss knows how to, once we have ascertained, once we have made clear that this column is really uniprot proteins, Edelweiss knows how to turn uniprot proteins into IRIs. So that can be RDF, and then you can export your data as linked data. But then also Edelweiss also knows how to fetch additional data about uniprot values. So it can give you an offering of a selection of extra columns that you can potentially bring in to enrich your data sets. So Edelweiss does that for you, and it fetches the gene name, this blue column here. So based on the uniprot protein, we were able to fetch from the uniprot data server additional information about that protein, and thus give you more contextual data for the original table. So that's first discovering data and then discovering column types. And based on one of the discovered columns here, we fetched one of several available optional columns. So this is kind of going a long way to giving you linked data with minimal effort, because now you don't have to type your IRIs manually, and you don't really have to tell the system what all the columns are. As much as possible, the knowledge base is trying to guess what are these ontologies, what are these IRIs, and what is the type of all this data here. It's also trying to provide you as much as it can with optional columns from secondary data sources. And everyday users, if they don't want to see these IRIs, they will see normal old style data, let's say, by default. So nobody will be confused, we hope. And you can generate and also maybe publish a linked data version of your entire data set with a click, or a non-linked data one if you prefer. So all these options will be available to you. And this is, I think, the missing cornerstone in the linked data pyramid that we have now put in place. So if you just need the old style data, we already had some tried and true DC solutions We had a data explorer, which gives you powerful searchability and navigability. We have the API access from Python, R, HTTP, and a bunch of other languages. We have versioning and provisioning that we're also working on for standard DC technologies. And for example, hashing a data set to ensure users always have the correct version. And these are important things to have for reproducibility as well, because if you can't make sure I have the right version of my data set, and if you can't have different versions, then reproducing some findings becomes a lot harder, and keeping a data set updated becomes almost impossible. So now we go back to the biological problem with these technologies in our bag to integrate LTKB and drug bank with Edelweiss to help study Rosiglitazone and see what we can find. So again, the Rosiglitazone case. Now, imagine we have a researcher who wants to understand Rosiglitazone. Is Rosiglitazone safe? There is a concern, and we want to find more information. The starting point is the LTKB dataset, the liver toxicity knowledge base, which is a public data set from the FDA. And there's a finding in LTKB that Rosiglitazone is less daily concern. So it's not totally safe. It is a low degree of concern, but it's non-zero degree of concern. And it's we also know that Troglitazone is structurally similar, and Troglitazone has most daily concern. So this makes us a little worried. So we are paranoid. So we would like to have more contextual information so we can begin our own investigation and start thinking a little more about this. So Edelweiss to the rescue. We use Edelweiss to first we load the LTKB dataset, as I did before, into the schema discovery, and then I get some extra columns from drug bank by using Edelweiss. So Edelweiss is suggesting the blue columns here, toxicity and absorption, based on the PubChem CID column. The PubChem CID in LTKB is the axis of integration, because that column was shared both by the LTKB datasets and by the drug bank datasets. And that's why Edelweiss was able to suggest columns of interest, such as toxicity and absorption. So the new information we found about Troglitazone by performing this Edelweiss integration was, well, we got this description, we got the mechanism of action, we got pharmacology, so fairly detailed natural language stuff. In addition, there is things like hydrophobicity, and there is half-life and various other things you can get in there. Literally more than 50 columns you can choose from based on what's interesting. For this demo, I chose these columns quite arbitrarily, but there's many other ones. But these still give you a lot of information about how does Troglitazone work, and that may help you in your work to give you some ideas about where should I go next to find even more information, and what kind of experiments do I want to run on Rosiglitazone based on what happens with Troglitazone. So we found, we knew from before, Troglitazone is structurally similar to Rosiglitazone, and Troglitazone is a failed drug that's been taken off the market. The detailed mechanism of action and pharmacology information about Troglitazone was discovered from drug bank by Edelweiss by using LTKB as a starting point. And this may suggest potential concerns for Rosiglitazone, and it may inform further investigation. So now going back to this dataset lifecycle image, Edelweiss is addressing these problems of annotation and publication and integration of data, hopefully bridging this gap from the all these trapped data sets that are trapped in the lab where they were generated, and hopefully giving you an escape raft so you can go away from your island and go out into the big world and do meaningful things with all the big civilizations out there by means of your applications, your study, your derived data set, and what have you. So we think that is a fruitful way to cross that chasm. For what I've said so far, I want to acknowledge Tissue Dynamic, who shared some slides with us, and the University of Mannheim Drug Bank Sparkle server that was used as a basis for the data integration I performed. Now, just to finish off this presentation and to give the final steps here, I want to talk about how these technologies can be used together with Garuda to do even more discoveries, and how there's a natural synergy between this kind of data discovery and the kind of analytics discovery that's already been well established in Garuda. So what are the strengths of Garuda? So Garuda provides you gadget and analytics discovery in a safe and curated environment. So you're supposed to work playfully, but within safe boundaries. It's trying to encourage your sense of experimentation in such a way that what you're doing is still a little bit valid and validated, so you can't do anything too strange. So it's trying to be a meaningful integration. And in a previous talk I've given a few years ago, I showed how to do pathway visualization with Garuda and OpenTox. And in that case, we were doing a couple of discoveries with OpenTox gadgets. So I was using the OpenTox sample finder to find samples in OpenTG gates, and then using the data fetcher to find gene expression data. Then I took a pathway database and visualized the pathway in the cell designer. And then I took the gene expression data finally and overlaid it onto the pathway to visualize how the gene expression changes over time in that pathway. So that was possible by combining OpenTox gadgets and Garuda gadgets that already existed. Now, if you combine this with the Edelweiss capabilities and the Edelweiss data discovery, what you can do, once we bring all these things into Garuda, you would have gadgets in Garuda for uploading data and for discovering additional data. Then you should be able to use the Data Explorer inside Garuda to filter and search and understand data and to discover more data. And then when you enrich your data sets, that can be a basis for additional gadget discovery. So for example, you might discover in my random data set, you can enrich it with gene symbols or with pathways or with geoterms or with compounds. And these enriched columns can then be used to discover more gadgets that you can use in Garuda and bring them to bear on your original data set that you brought in. So there should be a very natural synergy there in theory. So the aim with Edelweiss is to bring low effort linked data to any data set in a correct, simple, and easy way, and to automatically annotate anything in the life science domain as far as possible, and to discover data. And we applied this to Rosiglitazone to integrate additional information from drug bank with LTKB to enable a comparison with Troglitazone. And when we bring this to Garuda as well, we hope to get a unique synergy of gadget and data discovery, by which the enriched data sets should be able to let you use gadgets you would not otherwise have been able to use on your original data set in Garuda. So we think this is a very natural direction to go, both for Edelweiss and for Garuda, and for the OpenTox plus Garuda partnership. So thank you for listening. That's the end of the talk, and I will take your questions now.